Hello friends, welcome to HP Vibrant Academy. In the last lecture we have discussed up to question number 6, so we will discuss question number 7 onwards in this particular lecture. So basically we are discussing the problems on the Stokes theorem. So let's start our discussion. So what we have seen in the Stokes theorem is that Stokes theorem gives a relation between the line integral and the surface integral. So what is the basic expression for the Stokes theorem is f dot dr along the curve C is equal to curl of f dot n cap into ds. This is along the surface S. So this is the basic expression for the Stokes theorem. Okay. So the Stokes theorem, the important point here is we have to notice that the Stokes theorem is applied on a open surface such that a surface S is being bounded by a closed curve C. Okay. So the Stokes theorem is being applied on a open surface, okay, such that the surface S is being bounded by a closed curve C. Okay, so now let us take an open surface. Okay, this is an open surface. It is open from the bottom, and this is our curve C. This is our curve C, and this is our surface S. Okay, so this is our surface S, and this is open from the bottom, and this periphery is curve C. Okay, and the unit vector along the outward normal is in this particular direction. Okay, so the order of curve C will be as per right hand thumb rule. So as per right hand thumb rule, the order of the curve C is anti-clockwise direction. Okay, so let us understand this with a figure. So we have an open surface like this. This surface is open from the bottom. Okay, so this is our curve C, and this is our surface S. So as per the Stokes theorem, f dot dr along the curve C is equal to f dot n cap, curl of f dot n cap into ds. Okay, so this is our curve C, and this is our surface S. So f dot dr along the curve C is equal to curl of f dot n cap into ds. Okay, so this is the basic expression for the Stokes theorem. So let us start discussing the problems. Let us start discussing the problems. So in the question number 7, we have to show that verify Stokes theorem for f is equal to y I cap plus z j cap plus x k cap, where s is the upper half surface of the sphere. Okay, and the sphere is given as x square plus y square plus z square is equal to 1, and c is its boundary. Okay, so we have the sphere like this. Okay, and this is open from the bottom. Okay, and this is our xy plane. Okay, and this is x square plus y square plus z square is equal to 1. Okay, so along the xy plane, this will be z will be 0, so this is obviously a circle. X square plus y square is equal to 1. Okay, and let us solve this. So let us apply the Stokes theorem. So we have the Stokes theorem as f dot dr along the curve C. This is our curve C is equal to surface integral along the surface S, curl of f dot n cap into ds. Okay, let us find the value of curl of f. Curl of f is equal to del cross f, and this is equal to I, j, and k, and the value of f is y, z, and x. Sorry, let us write down the components of del. So this is del upon del x, del upon del y, this is del upon del z, and components of f are y, z and x. Y, z and x. This is equal to I cap. This is 0 minus 1 plus j cap. This is 0 minus 1 plus k cap. This is 0 minus 1. So this is minus of I cap plus j cap plus k cap. This is the value of curl of f. Okay, so now let us find this value and this value. So if both are same, then the Stokes theorem is verified. Okay, let us find f dot dr along the curve C. Okay, so f dot dr along the curve C. Okay, and the curve C is x square plus y square is equal to 1. Okay, so this is equal to, let us place the value of f. This is y I cap plus z j cap plus x k cap dot dr we can write as dx I cap plus dy j cap plus dz k cap. Okay, along the curve C, and C is x square plus y square is equal to 1. Okay, so let us further simplify this. So we have this as along the curve C, this is y dx plus z dy plus x dz. Okay, so on xy plane we have z is equal to 0. So z is equal to 0. This means this particular term is 0. And this is also 0. dz is 0. So we are left with y dx. Okay, so this we can write as y times of, in terms of parametric equation, we can write as y times of dx upon dt into dt. Okay, we can integrate this. So in terms of parametric equations, we have x is equal to cos t, y is equal to sin t, and t varies from 0 to 2 pi. Okay, so from here we have y is equal to, let us place the value, and this is t varies from 0 to 2 pi. The value of y is sin t, and dx upon dt, from here we have dx upon dt is equal to minus of sin t. Okay, so let us place the value. This is minus of sin t into dx upon dt is, sorry, value of y is sin t. Value of y is sin t into dx upon dt. dx upon dt is minus sin t. Minus sin t into dt, and this is 0 se 2 pi. This is value of I. So the value of I is equal to, let us take this as value of I. So we have taken this f dot dr along the curve C as I. So let us find the value of I. This is minus sin square t dt. This is 0 to 2 pi. Okay. So this we, let us further simplify this. So we have the value of I as minus sin square t dt. So sin t we can write as, this is minus of 1 minus cos 2t upon 2 into dt. This is 0 to 2 pi. This is equal to minus 1 by 2. This is dt. So this will be 2 pi. And this is minus of sin 2t upon 2. And this is 2 pi and 0. Okay, so this gets cancelled. So this is equal to minus of pi. Okay, value of f dot dr. Value of f dot dr is, minus pi. The value of this one is minus pi. Okay, now let us find curl of f dot n cap into ds. Okay, so for finding this, we have to apply the Gauss divergence theorem. So let us write down curl of f, the value of curl of f here. Okay, so we have the value of curl of f. Curl of f is equal to minus I cap plus j cap plus k cap. Okay, so now and the line integral we have found as f dot dr along the curve C is equal to minus pi. Okay, Now we have to find the value of surface integral along the surface S curl of f dot n cap into ds. This we have to find. So this is our curved surface and this is our curve C. This is our curve C and this is surface S. Okay. So now let us apply the Gauss. For applying the Gauss divergence theorem, we have to close this surface from the bottom. Okay. So let us understand this. Okay. So we have a hollow surface like this. Okay. So we have a hollow surface like this. So we are applying a Stokes theorem on this as f dot dr along the curve C. This is our curve C is equal to curl of f dot n cap into ds. So this is our surface S and this is our curve C. Okay. So f dot dr along the curve C is equal to curl of f dot n cap into ds. Okay. So this is a hollow section. So the Stokes theorem is being applied on the hollow section. Okay. Hollow surface. So now for applying the Gauss divergence theorem, we have to close this surface. So Gauss divergence theorem is being applied on a closed surface. So let us close this. Okay. So let us close this. So this is a closed surface. Okay. So let us consider the whole surface area of this body as S dash. Okay. So let us consider the whole surface area. The whole surface area of this surface as S dash. Okay. S dash is the whole surface area. Whole surface area of closed surface. Okay. And this white portion, that is this one, white portion, and there is a blue portion. Blue portion is the planar area. Okay. So this is white portion. White portion, that is this one. So S is this topmost surface. This is top surface. Top surface. And S1 is bottom surface. Okay. So S1 is bottom surface. This is the surface area of the bottom, and this is S1. Let us consider, and this is the top surface. That is white portion. That is white portion is S. So S dash is equal to S plus S1. Okay. So this whole surface area is S dash, and this is S, and this bottom surface area is S1. Sorry, bottom surface area is S1, and S dash is the whole surface area. Sorry, S dash is the whole surface area, S is the top surface, and S1 is the bottom surface. So we have S dash is equal to S plus S1. Now let us apply the Gauss divergence theorem. So from Gauss divergence theorem is being applied on a closed surface. Okay. So the Gauss divergence theorem is divergence of, sorry, f dot n cap into ds along the surface S is equal to divergence of f dv. Okay. Volume integral. Okay. So now let us replace f with curl of f. Okay. So let us place value of f as curl of f. So curl of f dot n cap into ds along the surface S is equal to volume integral divergence of curl of f dv. And from vector identity, divergence of curl of f is 0. So this is straight away 0. This is equal to 0. So now the value of s is, sorry, this is s dash. S dash. Okay. Because we are taking the closed surface now. So this will be s dash. Curl of f dot n cap ds. This is closed surface. So the Gauss divergence theorem is being applied on a closed surface. So we are taking S dash. S dash is the surface area of the closed surface. Okay. So curl of f dot n cap ds along the surface S dash is equal to divergence of curl of f dv, and divergence of curl of f is 0. So the volume integral is 0. So this means curl of f dot n cap into ds along the surface S dash. Okay. And S dash is equal to S plus S1. Okay. And this is equal to this is equal to 0. This is equal to 0. So now let us expand this. So this is equal to s plus s1. So curl of f dot n cap into ds along the surface s plus along the surface s1. This is curl of f dot n cap into ds. Okay, and this is equal to 0. So on the bottommost surface, so we have the unit vector along the outward normal as minus k cap. This is in downward direction. So we have this as planar surface. So the unit vector perpendicular to this planar surface is along the downward direction, that is minus k cap. So this will be, let us place n cap as minus k cap. Okay, let us further simplify this. So this is equal to along the surface S curl of f dot n cap into ds is equal to, this is minus, so this we can write as minus of surface integral along the surface S1. This is curl of f k cap into ds. Okay, this is equal to 0. So from here we have along the surface S, this is curl of f dot n cap into ds. This is equal to along the surface S1. This is curl of f k cap into ds. Okay, so now let us verify this one. So we have to verify the Stokes theorem. So line integral we have calculated, and from Stokes theorem, this line integral is equal to along the curve C f dot dr is equal to surface integral along the surface S, that is this one, top surface. Okay, this is top surface, curl of f dot n cap into ds, and this is equal to this one, curl of f k cap into ds along the surface S1. So this is equal to, this we can write as curl of f k cap into ds along the surface S1. Okay, so now let us further simplify this. So we have f dot dr along the curve C, okay, is equal to surface integral along the surface S, curl of f dot n cap into ds, and this is equal to, using this one, let us take this as equation 1. Using this, this is equal to surface integral along the surface S1. S1 is the bottommost surface, that is planar surface, curl of f dot k cap into ds. Okay, and this we have calculated as, the value of this one is minus pi. So we have to show the value of this one is minus pi. So let us show this. So we have along the this is curl of f dot k cap into ds. Okay, so along the curve C, f dot dr is equal to, this is along the surface S1. Let us place the value of curl of f. Curl of f is minus I cap plus j cap plus k cap. Sorry, this is minus is outside. Dot k cap into ds. So this is equal to minus k cap into ds along the curve, closed curve S1. Okay, sorry, this is dot product now. So this is k cap dot k cap is 1. So this is, and minus is there. So this is minus 1. So minus 1, and this is along the surface S1. This is ds. So this is equal to minus of S1. And S1 is the surface area of the bottommost surface. And bottommost surface is a circle. And the equation of this is x square plus y square is equal to 1. So area of circle will be, area of circle is pi times of 1 square. So this is equal to minus of pi times of radius square. Radius is 1. This is equal to minus pi. Okay, so the value of line integral is minus pi and value of the surface integral is minus pi. So the Stokes theorem is being verified. Okay, so now let us discuss question number 8. Let us discuss question number 8. Verify Stokes theorem for this one. X square plus y minus 16, x square plus y minus 4 I cap plus 3xy j cap plus 2xz plus z square k cap, where S is the upper half of the sphere, x square plus y square plus z square is equal to 16 and C is its boundary. So let us solve this. So the value of f is given as question number 8. The value of f is x square plus y minus 4 I cap plus 3xy j cap plus 2xz plus z square. Okay. So from Stokes theorem we have f dot dr along the curve C is equal to curl of f dot n cap into ds along the surface S, and based on the result in the previous question, this we can write as this is equal to surface integral along the surface S1 curl of f dot k cap into ds. Okay, so this is our surface. This is our surface which is open from the bottom. Okay, and this is surface S, and the bottommost surface area is S1. Okay, and S1 is a circle. Okay, so the equation of this is, the equation of the sphere is x square plus y square plus z square is equal to 16, and the equation of circle is x square plus y square is equal to 4 square. Okay, so the value of S1 will be, S1 is the surface area of this circle. So circle is x square plus y square equal to 4 square. So pi into 4 square is equal to S1. S1 is equal to 16 pi. Okay, so now let us find the value of curl of f dot k cap into ds. So we have f dot dr along the curve C is equal to, let us write down this one. So this is equal to along the surface S1 curl of f dot k cap into ds. So let us find the value of curl of f. So curl of f is equal to I, j and k. This is del upon del x, this is del upon del y, and this is del upon del z. Okay, so this is x square plus y minus 4, this is 3xy, this is 2xz plus z square. Okay, so this is equal to I times of, this is del upon del y of this one, there is no term of y, so this is 0, and this is also 0, del upon del z of 3xy plus j cap plus j cap, this is del upon del z of this one, this is 0, minus, this is del upon del x, so this is 2z plus k cap, this is 3y, and this is del upon del y of this one, this is minus 1. This is the value of curl of f. Okay, so from here we have this as along the surface S1, and curl of f is this one, this is minus 2z I cap, and this is plus 3y minus 1 k cap dot k cap into ds. So this is equal to 3y minus 1, there is no term of this is dot product with k cap, so 3y minus 1 into ds. Okay, and this is along the surface S1, and S1 is a circle of radius 4, so this is x square plus y square is equal to 4 square. This is the value of line integral f dot dr. Okay, so in terms of parametric form, let us write down the circle. So x square plus y square is equal to 4 square, so this is a circle of radius 4 unit. So in terms of parametric form, this is x is equal to cos theta, 4 cos theta, and y is equal to 4 sin theta. Okay, and this ds we can write. Let us take an elemental area here, elemental area at an angle of theta. So this is theta, so this is d theta, and this is r, so this is dr. So this area will be r d theta into dr, that is r dr d theta. Okay, so this we can write as 3 times of value of y is 4 sin theta. So 3 times of 4 sin theta, that is 12 sin theta minus 1 into r dr d theta. Okay, so from this circle we have r varies from 0 to 4, r is equal to 0 to 4, and theta varies from 0 to 2 pi. Okay, let us further simplify this. So this r dr, so the integral of r dr is r square upon 2. Okay, so this is equal to r square upon 2. Let us take this as line integral f dot dr. So this is equal to r square r dr, that is r square upon 2, that is 4 square upon 2, 4 square upon 2 into theta is equal to 0 to 2 pi, and this is 12 sin theta minus 1 into d theta. Okay, so this is 8 times of this is 0 to 2 pi, this is 12 sin theta d theta. Okay, the integral of sin theta is minus cos theta, so this is 12 times of minus cos theta, and the limit is 2 pi or 0, and this is minus of theta, and limit is 2 pi and 0. Okay, so this will be 0 because cos 2 pi is 1 and cos 0 is also 1, so this is 0, and this is equal to 8 times of 2 pi, so this will be equal to minus 16 pi. Okay, so the value of surface integral is minus 16 pi. Value of surface integral, this one is minus 16 pi. Now let us find the value of line integral for verification. So we have this as along the curve C f dot dr is equal to, let us write down the value of f. This is x square plus y minus 4 I cap plus 3xy j cap plus 2xz plus z square into dr. The value of dr is dx I cap plus dy j cap plus dz k cap. Okay, so let us further simplify this. So this is along the curve C. So this is x square plus y minus 4 times of dx plus 3xy into dy plus 2xz plus z square into dz. Okay, along the curve C. So on curve C we have the equation as, on curve C is a circle of radius 4 unit. Okay, so this is curve C is x square plus y square is equal to 4 square. So on circle C we have the value of z as 0, so there will be no term of z, so this is 0, straight away 0. So this we can further represent as, we can divide this whole expression upon dt and we can multiply with dt. Let us divide this by dt and let us multiply this by dt. So in terms of parametric form we have x is equal to 4 cos t, y is equal to 4 sin t. Okay, and we have the t varies from 0 to 2 pi. Okay, so let us place the limit here. So this is 0 to 2 pi and this is x square. So x square is 16 cos square t and y is plus 4 sin t minus 4 into dx upon dt. So dx upon dt is minus 4 sin t. Okay, plus 3xy. So 3 times of xy. So this is 4 cos t, this is 4 sin t. This is 16 cos t sin t and 16 times of 3. This is 48. So 48 cos t sin t. Okay, whole dt. Okay, this is the value of line integral along the curve C f dot dr. Okay, so on simplification we will get this as minus 16 pi. Okay, so the value of line integral is value of surface integral is minus 16 pi, and value of line integral is also minus 16 pi. Okay, so the Stokes theorem is verified. Okay, now let us discuss question number 9. Let us discuss question number 9. Verify Stokes theorem for f is given by this particular expression where s is the upper half surface of the sphere, x square plus y square plus z square is equal to 1, and c is its boundary. So it is similar to question number 8. Let us solve this quickly. In question number 9, we have the f is equal to 2x minus y I cap minus yz square j cap minus y square z k cap. Okay, and s is the upper half surface of the sphere. Upper half surface of the sphere. Okay, and the sphere is x square plus y square plus z square is equal to 1. Upper half surface of the sphere, and c is its boundary. This is the c. Okay, and this is lying in the xy plane. This is x, this is y, and this is z. Okay, so the equation of curve C will be a circle, as z is 0 here. So x square plus y square is equal to 1. Okay, so let us write down the expression for the Stokes theorem. Okay, so this is our surface S. So we have line integral along the curve C f dot dr is equal to surface integral along the surface S curl of f dot n cap into ds. Okay, and this is equal to along the surface S1. S1 is the bottommost surface. S1 curl of f dot k cap into ds. Okay, so the proof of this we have already discussed in question number 1. Okay, so now let us find this. So let us find the value of this one. So this is equal to surface integral along the surface S1. Let us find the value of curl of f first. So curl of f will be curl of f. This is equal to I, j and k. This is del upon del x, del upon del y. This is del upon del z. Okay, and we have this as 2x minus y. This is minus yz square, and this is minus y square z. Let us find the value. So this is equal to I times of this is del upon del y of minus y square z. Okay, this is minus 2yz. This is del upon del z of this one. So this is plus 2yz plus j cap plus j cap. This is del upon del z of this one. So this is 0, and this is also 0 plus k cap times of this is del upon del x of this one. This is 0, and this is del upon del y of this is 2x minus y. This is plus 1. This gets cancelled. So this is equal to k cap. Let us find the value of this one. So we have f dot dr along the curve C is equal to, let us find the value. This is equal to this one, curl of f dot k cap into ds along the surface S1. Let us place the value of curl of f. Curl of f is k cap times of k cap into ds. So this is equal to S1, and S1 is equal to pi times of k cap. This is equal to pi times of radius square, 1 square. Radius is 1, so this is equal to pi. Okay, so the value of this one is pi. Now let us find the value of f dot dr along the curve C. Let us find this one. So f dot dr along the curve C, this is equal to 2x minus y I cap plus, sorry, this is minus y z square j cap minus y square z k cap into dr is dot dx I cap plus dy j cap plus dz k cap. Okay, along the curve C, and the C is a circle of radius 1, x square plus y square is equal to 1. So this is equal to 2x minus y dx minus yz square dy minus y square z dz. Okay, so on the circle C, on the circle this one, x square plus y square is equal to 1, we have, there is no term of z here, so this is 0, this is 0. So we have 2x minus y dx, okay, along the curve C. This is the value of f dot dr. Okay, so in the terms of parametric equation, this we can further simplify this. Along the curve C, this is 2x minus y, this we can write as dx upon dt into dt. Okay, so in the terms of parametric form of the circle, we have x is equal to cos t, y is equal to sin t. Okay, and dx upon dt is minus sin t. So this is equal to, and t varies from 0 to 2 pi on this circle. So this is 0 to 2 pi. This is 2 times of value of x is cos t minus, this is y. So y is sin t into dx upon dt is minus sin t into dt. Okay, so this is equal to sin square t minus 2 sin t cos t. 2 sin t cos t is sin 2t into dt. This is 0 to 2 pi. Let us further simplify this. So we have this as sin square t, we can write as 1 minus cos 2t upon 2 dt. This is 0 to 2 pi. And this is minus of sin 2t is integration of sin 2t. This is minus cos 2t. This is plus. So cos 2t upon 2. This is 2 pi and 0. So cos of 4 pi and cos of 0 is same. So this is straight away 0. So this is equal to half of, this is 2 pi minus of half of cos 2t is integration of cos 2t is sin 2t. Sin 2t upon 2. This is 2 pi and 0. So this is also straight away 0. So we are left with pi. Value of this one is also pi. Okay, so value of f dot dr along the curve C is pi, and value of the surface integral is also pi. So the Stokes theorem is getting verified. So we have discussed up to question number 9. So we will discuss further questions in next particular lecture. Thank you.